Okay, many aspects of about programming languages, theory, semantics, language design, parsing techniques, IDEs, editors. And recently I've been more active in source-to-source transformation, especially in the context of migration of legacy applications. Typically older applications written in COBOL, PL1, RPG, these kind of things, that we try to move to modern computing environments such as Linux servers and modern languages such as Java. I do this with a company called LZ Labs. If you're interested in such topics, we have a career page where there are always a few openings, so don't hesitate to have a look if you want. And you can also contact me directly. What I'm going to talk about today is an old project that I did with a startup company called ATG that doesn't exist anymore, unfortunately. It all started with the idea that we saw a lot of DSLs, namely domain-specific languages, starting very small, often written in-house, and growing over time. The common pattern is that you start designing your own small DSL for your small own domain application, your small problem. And after a while, users come back to you and they say, well, I would like to be able to print something. So you add statements to your small language. And a while later, they come back and they say, well, I would like to be able to compute 1 + 2. So you add expressions to your language. And then they come again and they tell you, well, you know, my code is getting large, it's difficult to maintain. So you add functions or classes or modules to your language. And your small domain-specific language ends up into something almost as large as Java, but it was never designed to be large in the first place. It's poorly maintained, and you're stuck with it, and it's a source of major problems. So we thought we could do things the other way around, namely starting with a general purpose language, such as Java, and then adding the features that we need for our specific domain. So we did a dozen experiments, and 2 of them became products. The first one is OptimJ. It was about describing optimization problems, scheduling problems, and the main idea was that we added to Java the notion of logical variables, the same kind of variables you find in Prolog, for instance. The second one, the one I'm going to talk about today, is a PX. This stands for parallel extension, and it provides addition to express parallel programs. So there are many models of parallelism out there. The one you all know about is threads. But threads is a very low-level concept. Threads is what you find on the metal in the processor. And unfortunately, this is the model that has been mostly exposed in higher-level languages. It turns out that the model of threads is very badly suited to write parallel programs, to the point that someone wrote an entire book about the problems with threads. Another common model is task parallelism, where the most common activity is to launch threads. You probably have heard of Erlang. A typical Erlang program is going to launch millions of threads. There is message passing. This MPA stands for message passing interface. This is something you find in scientific computing. This is used in the huge supercomputers that the physicists used to do simulation, weather simulation or this kind of things. There are thousands of computing nodes, and MPI is used to manage the routing of messages between all these nodes. Another common model is OpenMP for data parallelism. So this one is a bit funny. It comes as pragmas for C or C++. And the idea is that you're going to write your program in C as usual, and then you will add annotations to tell the compiler that no, after all, this should be running in parallel. So it's a bit strange in the way that you first have to sequentialize your program. You can write a C for loop, which is sequential in nature, so you need to sequentialize your program. And in the second step, you say that, oh no, after all, that was not sequential, please run it in parallel. But it works pretty well, and it's used widely. The last model is more academic. It's called the process algebras. Two common examples are CCS and PyCalculus, so they are used by academics to write papers, but they have always been used in a programming language that probably nobody has heard about, which is called OCaml. An algebra means having composition operators, and this is going to be the main idea of this presentation. So ATGPH is based on this idea from PyCalculus. It provides composition operators to compose parallel branches. So what are compositional operators? You can think of this as sequential composition. Right? You first do the statement on the left. When it's done, then you do the statement on the left. So you take two statements and you combine them in a new statement. Actually, you can do the same for parallel composition. Okay? So we introduce, this is new, right? This does not exist in Java. We introduce a new operator, and the meaning is, well, do this and that at the same time. And the statement would be terminated when both are terminated. It's compositional. You take two statements and you build a new statement from it. Notice that all the other model of parallelism that I've mentioned before are not compositional. And that is going to make a big difference. So what kind of things can we express with this? This is an example of data parallelism. We have this parallel operator, and instead of just having two statements, A parallel B, we have, how is it called again? We have generators and filters, so we are going to have many branches in parallel. This says that for all I, all j, and I plus j less than n, we increment the element of a matrix. This defines the lower, the lower left triangle in a matrix. And all these elements are going to be incremented in parallel. There is a special case of this, which is the parallel for operator, where you basically take a standard for operator and you add just one parallel bar, and then your for loop is run in parallel. It's the same as the above, it's just a syntactic convention. A fun example is recursive parallelism. You all know the Fibonacci function. This is the Fibonacci function, except that every recursive call creates a new parallel branch. So you start with one branch that creates two parallel branches, then you have four parallel branches, and so on and so on. So assuming you have you have unlimited computing power, you would end up with lots and lots of branches. Speculative parallelism means that you're going to launch things. Again, assuming you have enough computing power, you are going to launch, in this example, 2 sort algorithms. And you don't know which one is going to be faster because it depends on what is the data, the actual data inside the array. So you launch both of them in parallel, and then you take the first result and discard the other. What's interesting here is the return statement inside the parallel branch. The return statement says that, okay, this is going to be my result, and please discard all the other branches. Stop them and discard them. Written this way, it's very concise and intuitive. If you have ever written parallel code, you probably know that properly terminating branches is very difficult to get right. Typically, when you have an exception inside a parallel branch, there is something that's difficult to manage. Here, the compiler is doing everything for you. Reductions are a very common thing in data parallelism. Here, the sum of square, you apply the sum of the plus operator over a collection of elements, so over all I squares. So this is the sum of all I squares, except that it's done in parallel. It's called a reduction because you start with a lot of data and you reduce it to only one result. So you have reductions on values, where the operators are going to be the sum, the product, this kind of things. Or you can also have reductions on collections, where you can build in parallel the set of all names of a given set of persons. This was done before the Java streams, so we might do this. If we did this today, we might do it in a different way, maybe. But this is different than streams in the sense that it's an algebraic description. Algebraic in the sense that you provide an operator to operate on data, rather than just an operational description. So when you talk about parallel programming, the first question that people ask usually is performance, because that's the main reason. It's not the only reason, but it's the main reason why people use parallel programming. It turns out that this is almost as fast as writing directly threads. Here in this example, you have the same code on the right side, on the left side, and they have very similar performance. This is an example of matrix multiplication. Basically, you have 3 embedded for loops. And it's a bit complex because if you want to get performance, you need to block. You cannot have a thread. You cannot have a new thread for each single element of the matrix. You have to operate on blocks. So the left side provides all the machinery to operate on blocks. So these two programs have more or less the same performance. The big difference is that if you want to experiment and say, okay, I would like to block in a different way, or instead of running the outer loop in parallel, what if I run the inner loop in parallel? With the PX version, doing this kind of experimentation is very easy. You just move your parallel operator to a different place, and you see if your performance improves the trees and so on. If you look at the problem on the left side, you have to rewrite the entire code in a totally different way. Yeah? So even though the performance itself is similar, I claim that you get better performance with this more higher level description of parallelism, precisely because it makes it easier to think at a higher level. It makes it easier to try and to experiment with different ways of parallelizing. So another aspect of parallel programming is distribution. When you have one program here, another program there, and they must communicate. So there must be some notion of message passing. Here we have a channel declared. It's just a Java variable of type chan, and we can send, using the band operator, we can send a message over the channel, and with the question mark operator, we can receive a message on the channel. So in this example, we have two parallel branches, okay, two pieces of code running in parallel. One is sending a value on the channel, the other is reading a value from the channel and then printing it. There is non-determinism in this. In this example, we read a value on channel 1 and we read a value on channel 2 in parallel. So this is not about performance. This is really about semantics. The semantics of the program says that the values can come in any order. And in the end, you will have read the two of them. You may read the value 1 first, or you may read the value 2 first, and then the other one. So in this example, parallelism really adds something to the semantics of the language. We have another kind of non-determinism which commits on a choice. So if a value is available first on channel 1, then we commit on this value, we print it, and we forget the other branch. If a value is available on channel 2 first, then we read this value, print it, and we forget about channel 1. And this is typical of a server accepting connections. Or if you know system calls, this is exactly the select system call in Unix. With the same constructs, we can also emulate other models of parallelism, such as data flow or actors. This is an example of data flow, another in the data flow style. Another is going to read two values from two input channels, okay, C1 and C2, not in a specific order, in any order. If you impose an order, if you impose that you first read from the first channel and then from the second channel, you may end up in a deadlock because the values have actually come in the other order, in the opposite order. So you read the two input values, do a computation, and then send the result on the output channel. We can also have annotations to locate parallel branches to other places. So using the IP annotation, we can locate one parallel branch on a different machine somewhere on the network. So this is the same example as before, where we send a value on a channel, read it, and print it, except that the first branch is going to run on the machine at address 2. On that machine, it will send a message on the channel. The second branch will run on a different machine at address 3. It will read a value from that channel and print it. So the same program, just by adding annotations, can be either run locally or distributed among a network. Interestingly, we can use the same mechanism for GPU computing, where we have another annotation, here it's called OpenCL, that says that that tells to locate the branch on the GPU. And what's interesting here is that a GPU, a typical GPU has a hierarchy of kernels, a hierarchy of memory and processors, just as in the picture here. And what's interesting is that this hierarchy is reflected into the lexical scope of the program. When you write code directly in OpenCL or CUDA, which are the two standard languages for GPU programming, you need to locate your code at some level in some kernel, but you do this in a very ad hoc way. So an important question about parallel programs is correctness. As soon as things run in parallel, it's terribly easy to make mistakes, and it's terribly difficult to debug them. When you code using threads, you have this notion of thread safety. Thread safety is not exactly the right notion. Thread safety applies not to one specific composition, not to one specific program. Thread safety applies to one method or a set of methods. So in a sense, it's way too much. We don't need that much. We need to prove that one given composition is safe. We do not need to prove that that a given method in any context is safe. So this is way too much, and it's also in turn very difficult to prove. When you want to check correctness of a threaded program, you need to basically look at the entire program. You cannot just you cannot make a local proof. You need to look at everything. This is the main difference when you have compositional operators. You only need to prove the correctness of parallel composition at the point of composition. If you have a method that is not used inside a parallel composition, you don't care whether it's thread safe or not. Okay? It's really the composition. So it's local. It's very specific to that composition, and this makes it possible to automatize the proof. So not in general, but it can be somewhat automated, or you can have the compiler or a given tool to tell you, well, be careful here, there might be a problem about parallel composition. So this program extension is based on a theoretical model which is called PyCalculus. All the operators I introduced here come from PyCalculus. So the parallel bar operator, the selection operator, and message passing, sending a message, receiving a message, everything comes directly from PyCalculus. And this was very helpful. So first, I think it makes things very, very concise and rather intuitive. It was also very useful in doing the implementation because there are very, very tricky cases where you don't know exactly what the behavior should be. So in this case, the answer was simple. Look at PyCalculus and what would PyCalculus do in this case. So it was a huge help for us to do the implementation. I've been talking too fast. You will have a large break. So once again, there is one. If there is one word you should remember from this presentation, it's the word compositional. It's really the fact of having compositional operators that makes things concise and intuitive. And no other model of parallelism has this. It's efficient. It's integrated in the language. So being we would not have been able to do this just with an API, with a library. Okay? But being integrated in the language and offered as a language extension has a number of advantages, but it's also very difficult. Adoption is difficult because people are reluctant to become dependent to a new language. It's much easier to adopt a new library, a new API. Yeah. Then there's a problem of tooling support. It's a different language. It's not Java anymore. It's an extension of Java. So the tools, all the development tools that need that require Java source code as input would just complain that there are syntax errors. So the way we implemented it was not as a compiler that generates bytecode. We implemented it as a source-to-source conversion from extended Java to standard Java, so that all the tools that need to input all the tools that need Java code as input would still work with this. But this means a lot of work. Especially for the editor support, the debugging support, and so on. And another problem for which we don't have a really clear answer is the compatibility between different language extensions. We also have this problem with APIs, but it is solved by naming conventions. As long as you start your API with your own name, with the name of your own company, then you can rest assured that nobody else will use the same name, so there will be no conflicts. In the case of language extensions, it's more difficult than this, and we were not able to come with a general solution. In terms of implementation and efficiency, this project would benefit a lot from the lightweight fibers that are currently in preview in Java. When you create threads, you can make your system die with just hundreds or 1,000 threads. With lightweight fibers, you can have millions of lightweight fibers without any problems. So if you're curious about this, there's a lot of documentation and code samples on my GitHub repository. this was a product we did a few years ago, and it's not maintained anymore. But if you want to build upon it, if you have a student and you want to do a master project about this or something, a number of pieces are available. One important piece is the synchronization core to manage all the synchronization between incoming and outgoing messages. Just ask me if you want to use it. It's available. And the same ideas could apply to any. It's just not about Java. Java is an example of a language extension in this case. The same ideas could apply to any other modern language. Okay? So you're welcome to reuse and extend this. And I'm over. It's time for questions if you have on Slido. And I don't see any question on Slido. Yeah? On 12?
We have here Q&A.
Q&A.
And that's the questions.
What is a branch? We had a dilemma about naming things. We didn't want to, when you run two things in parallel, we didn't want to call them processes or tasks or threads, because all these terms are heavily connoted. They are used in a specific context with a specific meaning, and nothing was really what we meant. So we used the term of branch to mean something we run in parallel that could be implemented by a branch. It could be implemented. It could be implemented by a thread. It could be implemented by a process. It could be implemented by some remote code. It's a way to express that it's a semantic meaning that is independent of the way it's implemented. Does GPU work directly when we use it in Java? So GPU, you cannot run a JVM on GPU. So there are strong limitations on what can be run on the GPU. The idea is that we convert the Java code to OpenCL code. And if there are things that are too complex that are not available in OpenCL, then it's not going to work. Is it compatible with all Java versions? Yes, because it's done at the language level, so it doesn't really care about it's unrelated to runtime version. It's related to language version in the sense that whenever there's something new at the language level, then we must follow and implement this. This is another problem of doing language extensions, is that you're always running after the new versions of the main language.